Hi, once again, welcome to non-homogeneous boundary value problems. Okay, in this chapter, to solve non-homogeneous problems, and the first time we're gonna deal with is time-independent PDE boundary conditions and boundary conditions. So, for example, we have this problem here. This problem is non-homogeneous because you can read more about non-homogeneous and homogeneous PDEs in the textbook and know more about that. So I'll be just solving problems and focus on separation variables so you can just read the definition. Okay, as you can see, uh, we have this problem here. This problem, you actually can recall it from the heat equation of a road. Let me just, the heat equation of a road. If you have a road that is bounded here, you have here the temperature is 0, and here the temperature is also 0. And this heat equation, the one we did, the heat equation was pretty much like we didn't consider the heat that was generated inside the road. But here, the road itself, due to could be due to whatever like external factors, we get like it generates a heat generated, and this heat is added to the left part of the equation that we have here that was underlined. So this heat, for example, here this generated heat source was like A or power heat minus beta x. So could be that okay, this heat generated is due to the decay of the material of the road. So either the case, okay, you have to analyze and solve that problem. So this problem is non-homogeneous because we have some some function that is there that is not, usually we just had like a derivative of position in time, but here we have extra function that is not like derivative of u, so it's just some function. Okay, that means that is non-homogeneous. For homogeneous, we have 0 here. We don't have any function. We don't consider the heat generated by the body, or like the heat generated by the rod, or the temperature generated by the rod. Okay, now this problem is time independent PDE. Time independent because the boundary conditions, or like the non-homogeneous term, is just dependent in the position. It's not dependent in time. For example, this function here, a times e minus beta x, there's no time here. It just depends on x. And then we also look at boundary condition. Boundary condition 0, 0. So they are just constants. So they don't depend on time. So that means this is time independent PDE. Okay, to solve time independent PDE, uh, well, it's a long process, but we are gonna actually deal with it like slowly to see. Okay, first thing you want to have your boundary conditions to be 0. In this problem, the boundary conditions are 0. Okay, so I can just start by actually solving the problem. Okay, first step, this step is for boundary condition for time independent problem PDE. Since we have the both of them 0, we have here 0 and here 0. So I just have solution. Okay, first step. What I say? First step. The same way I did in the video, I think it was 13.3, the third video, if I remember, when I solved for non-zero boundary condition. Actually the same process. I'm gonna introduce u position time. I'm gonna introduce has to be equal to v position time. Since it is independent, just some function phi that depends only in position, because this is time independent. So this function phi just depends on position. Yeah, if I do that, then I have to sub this into the equation that I have. But before, I have this term, the equation, I have this, and I have this. Okay, I'm gonna find the first derivative, x delta v delta x plus derivative of phi respect to x. Then I'm gonna find second derivative u x squared, second derivative of v x squared plus second derivative of phi. Then I need also for time, u for time equal delta v delta t plus phi. It just dependent of it just depends on x. That means when I find derivative respect to times gives me 0. So I just end up with delta v delta t. Okay, that's the first step. Second step, okay, I'm gonna say this is equation 1 and this is equation 2. Okay, you need to sub 1 and 2 into the original equation, into the PDE. Okay, but doing that you have k. Second derivative is gonna be, you need to sub 1 plus a has to be equal to delta t, like that. Okay, now you have k there's k delta v delta t. Okay, now the third step, you make it into two problems, right? You have to separate them into two problems. Okay, I'm gonna say I want to solve the classic heat equation that we actually know how to solve. So I'm gonna select this has to be equal to this. I'm gonna say, okay, this has to be equal to this. But for that to happen, only if this term equal to 0, right? Because if this term equal to 0, then you have that this equality is true. So you have k plus a equal to 0. So you just have two problems. So you have to solve the first one for v, the second one for phi, and then just remember that the general solution is v plus phi. Okay, now to solve this, you need the boundary condition and initial condition. And to solve this, you also need that. Okay, from the problem, I have that u u0t equal to 0, and I have that u1t equal to 0. I know that uxt equal to v xt plus phi x. Okay, for the first boundary condition, u1, 0t has to be equal to v 0t plus phi x is 0, has to be equal to 0. Okay, for that to happen, I'm gonna say, okay, I'm gonna force, for the PDE, usually we want to have the boundary condition to be 0, right? So I want this to be 0. That implies that phi has to be 0. So I have 1 already. Phi 0 equal to 0. And that leads to v 0t equal to 0. Then I do the same for 1t equal to 0. And you end up v 1t equal to 0, which implies phi 1 equal to 0. Then you have phi 1 equal to 0. And here you have v1t equal to 0. Now for the PDE, you need one more condition, the initial condition. The initial condition, you have u x 0 equal to phi x, a function of x. Okay, from here, you have to isolate vxt equal to uxt minus phi x. That means vx0 equal ux0 minus phi x equal ux0 is fx minus phi x. That is your initial condition. Initial condition is when you have x0 has to be equal to fx minus phi x. Okay, that's the third step. So you pretty much have two equations. You have one problem to solve and two second problem to. So you need to solve them separately and then just you add them to get your u. That's all. Okay, I'm gonna solve two. Okay, fourth step. Solve 2. Because you need phi for the initial condition here to OV. So solve second. To solve the second is just a normal ODE, second order. You have plus a minus beta x equal to 0. Yeah, that's the equation. So you have k phi minus a beta x, second derivative, minus a over k beta x. Okay, so just integrate twice. For the first integral, you get this is a constant, so you're gonna get minus beta plus c1 like that. Then for second integral, you're gonna get, okay, all of this is just a constant a over k beta. All of this is just a constant. Then you integrate, you get e beta x over minus beta plus c1x plus c2 like that. Then you have that phi x equal to minus a over k beta squared e minus beta x c1x plus c2 like that. And that's your equation for phi. Now you need to solve for the constant. You need to solve for the constant c1 and c2. Okay, just now you need to use these conditions here that we have. The conditions that we have, phi 0 equal to 0. If I use that, I get phi 0 minus a over k beta squared e to the power of 0 gives you 1 plus c1 times 0 plus c2. Then you get c2 equal to a over k beta squared. Then you need phi 1 equal to 0. Then you have phi 1 minus a k beta squared e minus beta. Then you have plus c1 times 1 plus c2. c2 is a over k beta squared, has to be equal to 0. Isolate c1, a k beta squared e minus beta, and then you have minus a over k beta squared. Then from you have C1 and C2, so then phi x equal to minus a over k beta squared e minus beta x plus C1 a e minus beta minus a k beta squared x plus C2 k beta squared. Then phi x equal, you just have, you can isolate, you can factorize k, then you end up with like that plus and plus like this. And that's your phi x solution. Now you need to solve for v. To solve for v, step 5, v is just k delta v delta x squared equal to delta v delta t for v 0 t equals 0, v1 t equals 0, and you have v x0 equal fx minus phi x, like that, where phi x, all of that you found already. So this equation actually quite simple at this point. You can just watch my previous video. I solved this equation already. It's pretty simple. Okay, so after some work, you end up with this solution for v. Now you need to find an, so just use the initial condition, which x0 equal to the summation n1 infinity an e0 sine n pi x has to be equal to the initial condition, which was fx minus phi x. Then from here you have summation n1 to infinity an sine of n pi x equal to fx minus phi x. From here, an equal to 2 over 1, 0 to 1, fx minus phi x sine n pi x dx, where phi x you already have it. So you can just write vx t equal to the summation n1 to infinity an, what is an? 2 integral 0 to 1 fx minus phi x sine n pi x dx, then times, all of that is the an, then times e minus k alpha. What is alpha? Alpha is n pi sine of n pi x, n pi x. So that's your Vx. Now you just need to write your U xt equal to Vxt plus phi x. So Uxt will be equal to Vxt. Okay, I'm gonna start writing phi x. The only doesn't really matter. A k beta squared then you have minus plus x plus 1 then plus summation n 1 to infinity. You have 2 here, 0 to 1 fx minus phi x sine n pi x dx e minus k n squared pi squared t sine n pi x, like that. So this is your solution where phi x, this first term here, you also include it there. So the solution so the solution is actually a very long expression. It's a very long expression. So this is the solution. You can evaluate, you can see that when t goes to infinity after a very long time, the exponential term here goes to 0. Then you just have that uxt will approach to phi x. So the phi x is your steady state solution, because when after a very long time the Fourier term part actually vanishes. Since this part vanishes, you just end up with phi part. So that's your steady state solution. Yeah, so you can actually use this to evaluate many cases. It's quite complex, so you just have to know the steps, how to evaluate. Just follow these steps and you won't have a problem.